Hello everyone. In this video we will go through this example 5.4. We have a circular pipe with a radius capital R and it has a perforated section. This means that it has pores on this section, so that we have water discharging out through this section and all over the pipe, so that we don't have just two outflows like this, but all around the pipe we have those pores. It is given that we have constant velocity at this inlet, and the velocity distribution is given like this in the perforated section, and the average velocity given as V1, but we will not use this numerical values, but we will just use the letters. It is said that discharge per unit length of the perforated section is Qs. This Qs is given as discharge per unit length. So that we need to surely convert it to regular discharge. It is asked to calculate the average velocity V2 at section 2. This velocity is asked, and the difference between the mass flux rate of sections 1 and 2, so that this one is asked, mass flux at 1 minus mass flux at 2. This is also asked. So that let's go through. As you see, the magnitudes of the flow rates are asked, so that we will use continuity equation. And please note that in order to determine V2, we can just simply use volume continuity equation, because there is nothing related with mass or density. Even if we write mass continuity equation, it will result with the same as the volume continuity equation. So that let's write volume continuity equation, which equals inflowing discharge summation will be equal to the outgoing or discharges outflow. We have at section 1 inflow, at section 2 and at the perforated section we have outflow. Please note that for the discharge at the perforated section, if it will be a constant discharge as like this, and as this lowercase letter qs is defined as discharge per length, in order to convert that lowercase letter q to the regular q, we need to multiply this qs with L. But it is not constant. In other words, the distribution is not rectangular, but it is triangular like this. And we know that triangle is just a half of a rectangle. So that for this discharge distribution, Q will be equal to just QS L over 2, because it is a rectangular distribution. For section 1, we have constant velocity, so that it will be V1 pi r square equals V2 pi r square plus QS L over 2. From here, dividing both sides with pi r square, V2 happens to be V1 minus QS L over 2 pi r square. This is the result. What about part B? It said that the difference between the mass flux rate of sections 1 and 2, if you write mass continuity equation, just like this one, just like volume continuity equation, mass flux inflow summation will be equal to mass flux outflow summation, so that mass flux at 1 equals mass flux at 2 plus mass flux at the perforated section. From here we can see that mass flux at 1 minus mass flux at 2 equals mass flux at the perforated section, and this was asked, so that we are looking for this, and we know that mass flux is just equal to density times volume flux, which is discharge. So that discharge at the perforated section was obtained here, so that M1 minus M2 will be equal to rho QS L over 2. This is the result. For part B. Okay, let's go through with the next example, example 5.5. Here, a circular pipe is given again, and the velocity is not constant at the section now, but it is varying linearly. But please note that this is a circle, so that thinking about the cross section, we have maximum velocity here and minimum velocity all over this surrounding boundary. And the acting areas of the velocities are not same, so that we cannot treat this velocity as just a half of a rectangle, just a half of a constant velocity, because the acting areas of the velocities are not same. Surely we will find the discharge at part A, and let's go through how to obtain discharge at part A. General formula for the discharge is integral of u dA, and u is given as u max 1 minus r over r0, and dA for circular areas is 2 pi r dr. Integral boundaries from 0 up to r0, from the center up to the r0 up to the end. From here, discharge equals, please note that um is constant, 2 pi constant, take those out, 2 pi um. Inside the integral, distribute this r into the parentheses from 0 to r0, r minus r square over r0 dr. And this integral will be equal to integral of r dr is r square over 2 minus r cube over 3. We have one more r0. Integral boundaries from 0 to r0. Then the lower boundary of the integral is 0. All results 0. No need to write. Just write upper boundary. r0 square over 2 minus r0 cube over 3r0. Surely is cancelled. And this equals to 2 pi um multiplied by r0 over 6. Or, sorry, r0 square. over 6, or Q equals pi r0 square over 3. This is the discharge. As you see, it is not just simply maximum velocity times a over 2, because it is triangular, as I said previously. The average velocity is just average velocity is just discharge over area, Q over A, pi r0 square over 3 over pi r0 square, which equals over 3. This is average velocity. Mass flux is simply discharge times density, which equals rho pi r0 square over 3. Momentum flux, let me take those like this, because we don't need those anymore. Let's go through part D, momentum flux. Please note that this is momentum flux. Rho times V square dA, independent of the direction. If we need a direction, we are using V that N notation. But if we don't need a direction, if we are just dealing with magnitude, this is momentum flux formula. Now insert velocity here. What was velocity? times 1 minus r divided by r0, so that square of it will be like this. Instead of dA, 2 pi r dr again. Take the constants out, and the integral boundaries from 0 to r0. Constants 2 pi rho square, and taking this square, we have 1 minus 2r over r0 plus r0 square times r dr, and from here we have the first term r dr, and the integral of r dr is r square over 2. The second term is 2 pi r over r0 minus the integral of it is 2 r cube over 3 r0. The third term is r cube dr, integral of it is r to the power 4 over 4. Integral boundaries from 0 to r0. And applying the lower boundary will result with 0, no need to apply it. So that 2 pi rho square. Inside the parentheses we have, or let's write it like this, taking r0 square parentheses and taking r0 square out. Inside the parentheses we have 1 over 2 minus 2 over 3 plus 1 over 4, and making the operation, we will see that inside the parentheses this number equals 1 over 12. So that the result will be 2 pi rho square r0 square over 12, or rho pi r0 square square over 6. Okay, this is the momentum flux. And in part E, it is asked to calculate, let's continue from here, momentum correction coefficient beta, and we know that this coefficient is to be multiplied with the momentum flux if we are finding momentum flux by using the average velocity like this. If we are using average velocity rho average square multiplied by A, should be multiplied with this coefficient in order to be equate to exact momentum flux. So that by dividing those two, we can find out momentum flux. Rows can cancel each other. And at the top, we have this canceling rho pi r0 square square over 6. And at the bottom, note that average velocity was over 3 square, and area is pi r0 square. Those two cancel each other. Square over 6 divided by square over 9 gives us 1.5 as the coefficient. Okay, I hope those were clear, and let's stop the video here and see you in the